Welcome to this video on electric fields and work done, part of the particles topic for higher physics. In particular, we're going to look at the forces that are acting on charged particles within fields, starting with electric fields in this video. So what things are we covering today? We are covering a little bit about what charges are and electric fields are, the different types of fields, a definition for potential difference or voltage, the relationship between potential difference, work done and charge, and a way to calculate the speed of a charged particle in an electric field, which is something that you will be asked to do and given questions to do. So what is a field? Well, apart from fields where we keep animals, a field in terms of physics is a region or an area around an object where if we put something, we experience a force. And there are different types of fields that we have come across already. So gravitational field, if we put a mass in a gravitational field, it experiences a force. If we put something magnetic or another magnet in a magnetic field, there is a force experienced. And if we put a charge in an electric field, that will experience a force and move. So gravitational fields are forces that act upon masses. Magnetic fields produce forces that act upon magnetic objects, and electric fields are to do with charged particles. We can represent the field with some arrows. So this is a diagram. Now these charges are completely separate. So the picture on the left showing a positive charge and the lines moving away from there as arrows are showing the impact of putting a point charge. What's that? Well, that's a charge that we put next to that positive charge, and that charge is always a positive one, and so that would then, because light charges repel, the arrows are then moving away. Whereas the picture on the right, the arrows are moving towards the negative charge because a positive charge would be attracted to a negative charge. So that shows the direction of the field and shows the direction of the force. If we had more lines coming out radially, then we would have a greater strength of field that would be shown there. So on the left there, we've got a positive and a negative charge and the field pattern we've got. And on the right, we've got the field pattern for two charges that are alike. In this case, both positive charges. So same applies. The direction of the arrow on the line shows what a positive charge would do and which direction it would move in if it was placed at that position. So looking at the left diagram, if you place one in the middle between the positive and negative charges, it would be repelled from the positive and attracted towards the negative. So it would move towards the right. You can be asked to draw out these diagrams, but most commonly it might be a multiple choice question showing you the shapes of the field and asking you what charges would exist for those. Looking at the picture on the right, we've got two alike charges. If we placed our charge in the middle of these two, so somewhere here, let's say, then our charge would be repelled by the charge on the right because the charge we put in is always a positive one, and it would be repelled by the one on the left, so in fact it would stay stationary if the charges either side are equal. If one has a greater amount of charge, then that would exert more force, and so the field shape would be slightly different between the two. Between parallel plates, we have a uniform field. And we can see the field is uniform because the lines are equally spaced between each other. Now around the top of the plate towards the edge, the field no longer remains uniform and you get these curved lines at the top and at the bottom as well. So in the middle you have a uniform field, but at the edge, because it's at the edge, you get these distorted effects, and so the lines become curved. Notice again the direction of the arrow from the positive towards the negative, because it's the direction that a positive charge would move if you put it within that field. And a positive charge would move from left to right in this particular case, because the left plate is positive and the right plate is negative. What type of applications do we have with electric fields within them? Well, we have the old traditional television set. Won't be too many of those in your house, so if you have a flat screen TV, that's different technology. The oscilloscopes that you may have seen us use in class for looking at wave signals. Positive charges and electrostatic attraction used for spraying paint, for photocopying and printing, and for taking out particulates in smoke and things like that. All applications of electric fields and static electricity. So let's move on a little bit and say, well, what happens when we place our charge in our field? So the bottom picture shows that we've got a positive charge that's suddenly placed between these parallel plates. Okay, so we're not wondering where it's come from, we're just saying it appears there, what would happen? And it's going to experience a force that moves it to the right towards the negative plate, away from the positive plate. Because the field is constant, it's going to be a constant force, and it's going to gain energy, it's going to speed up, it's going to accelerate, because if something has a constant force, F equals ma says it's got a constant acceleration. Constant acceleration means it increases in speed. Increasing in speed means it gains kinetic energy. So putting that positive charge in there experiences a constant force because there's a constant field, there's a constant acceleration, and there's a gain in kinetic energy. Kinetic energy being half mv squared, where v is the speed. So there's an increase in speed, there's an increase in energy. If we move that charge to the left towards the positive plate, then there's going to be a repulsion there, so we've got to do some work, put in some energy to get it to move in that direction. And we can say that the work that we do to move that from the right to the left is equal to the gain in electrical potential energy that the charge has experienced. Okay, we could make an analogy between this and us. Let's say we're looking at the ground here. So here's our ground, and we've got a ball here. And if we lift up that ball up to there, we have a gain in potential energy. And potential energy, you will remember, is EP. And that is m times g times h. And that is also equal to the work done, EW. That was the force times the distance that is done. So in the same way, if we lift up something, it gains in potential energy and will fall back down again. The charge that we've got in our field here, the positive charge that we've moved it that way. What's then going to happen? Well, it can move back the other way. It can take that gain in potential energy and move to the right in the same way that our object can fall back down again. There's a change in energies. So we lift up a rock, we do some work to lift up our rock, our ball, it gains potential energy, we drop it, turns into kinetic energy. The analogy with the charge is we move our charge, our positive charge to the left there, we do some work on that, it gains electrical potential energy, it's then going to move back to the right and change into kinetic energy. This leads us to the definition of a volt, and a volt is defined as the work done in moving 1 coulomb of charge between 2 points in an electric field. Okay, so 1 volt could also be described as 1 joule per coulomb. At National 5, the only thing we needed to know about voltage or potential energy was it was a measure of the work done or the energy per coulomb of charge. So now we're saying this is actually the relationship here at the bottom there, that V, the potential difference or voltage, is equal to W, the energy, divided by the charge, or W equals QV, which is how the relationship is given to you on the relationship sheet. So what does this mean? Well, if you're asked what is meant by potential difference or what is meant by voltage, then you should describe that as the number of joules per coulomb. So if we're asked what is meant by a potential difference of 5 volts, you would say that's 5 joules per coulomb of charge. So as long as you say the joules per coulomb, that is sufficient. If you say joules per coulomb of charge, so much the better. So this is one of those particular definitions that have a particular meaning. In the same way, you might recall, if we think back to our work last year, you might recall that if we're looking at current, then current was defined as the number of coulombs per second, and that's coming from Q divided by T. So similarly here, V is W divided by Q, so that is the joules per coulomb. So you can use the relationships to help you with the descriptions and the words. Okay, so let's have a look at how we might do some calculations to work out some energies. So when a charge moves in an electric field, we've already seen that we need to do work to move it towards the way that it doesn't want to go, but the field will also do work on it to accelerate it in that other direction. And that work is equal to the kinetic energy that the charge gains. So our W, which is Q times V that we've seen before, is equal to half times M times V squared. Okay, notice there are two V's here. The one on the left is the potential difference in volts. The one on the right is the speed of the charge. So try and make it clear when you're writing these out to see the difference here. Otherwise, you're going to get very confused between the two. Okay, they can't cancel because they are different things. So let's look at a particular example. So at the top right of the screen, we've got a diagram, and we've got a charge that is in between two parallel plates. So we have our uniform electric field. We've got the arrows representing the field going from the right to the left. And we're going to move that charge from A to point B. Okay, so somehow that charge is going to move all the way across to this particular point here, having started right at this right on the left. Okay, so we notice at the top that we've got a potential difference of 2 kilovolts. So that's 2000 volts. And we've also got some other prefixes in here. So we've got this one here, micro, as well. So we have to take into account our prefixes as well as the other parts. Micro should be saying, that's 10 to the minus 6. Kilo, that's 10 to the 3. So we've got some questions. Calculate the electric potential energy gained by the charge in the system as it's moved from A to B. Okay, then we're going to release the charge and describe its motion. Then we're going to work out how much kinetic energy it's going to have when it gets back towards A. And we're going to work out how fast it's moving at that point too. Okay, so calculate the electric potential energy gained by the charge field system. So electric potential energy, well, that is going to be equal to the work that has been done on the charge to move it from A to B. So W is equal to Q times V. Q is 3 microcoulombs. V is 2 kilovolts. Multiply the two together, to get our answer at the bottom there. The charge is released from at B. It's going to move back to A because if you remember the diagram that we had, so there was our positive charge that we've now moved that way. However, this plate here is positive, this plate here is negative, and this one is B and that's A. So the charge is going to be attracted that way and repelled from point B that way. So being within the electric field and a uniform field because it's parallel plates, there's going to be a constant force due to that electric field. So there's going to be a constant acceleration towards the negative plate or towards A. Okay, it's important that you get the details. So you need to say there's a constant unbalanced force. You notice I didn't actually say that because remember, it's the unbalanced force that matters, not just the force that's acting, because the object will move in the direction of the unbalanced force. And we can also say that there's a constant acceleration. And then we have the direction. Determine the kinetic energy when the charge is at point A. So the kinetic energy that the charges can gain is equal to the work done on the charge. So it's the same answer that you had previously. In a similar way, if we go back to our lifting up a rock option, the potential energy that's gained lifting up that rock is equal to the work that you did to lift it up in the first place. When you release it, the kinetic energy that it gains before it hits the ground is the same as the potential energy as it fell, if you ignore any losses due to friction, of which there would be very few. Okay, so conservation of energy says that the kinetic energy the charge has going back to A is the same as it had when we added to move it from A to B in the first place. Okay, so the mass of the charge is 5 milligrams. Calculate the speed of the charge. So now we have the mass, we have the energy, and we need to work out V, the speed. So EK is half mv squared, and we solve for V. So substituting the numbers, remember it's V squared, and then square root that answer to give us our speed, which would be going back towards A. Okay, so these are really quite common questions that are asked for you to work out the work done, Q times V, to work out the energy that's been gained, which will be equal to the work done, whether it's electrical potential or whether it's kinetic energy, depending on which way you've moved it in the field. And then that is then equal to half mv squared to allow you to work out the speed of the charge at that particular point. Okay, so the things that we've covered, we've had a little review of charges in electric fields. We've discussed types of fields. We've got the definition of potential difference, the number of joules per coulomb. Remember that is coming from W equals QV and V equals W over Q. W being work in joules, Q being charge in coulombs, so joules per coulomb. And then we've used that relationship to work out the work done or the kinetic energy gained, and then we've made that equal W equals QV equal to the kinetic energy equal to half mv squared to solve. So we've got QV equals half mv squared, and we've solved for V to work out the speed of the charged particle.